Okay, let's check out how we do hypothesis testing. The core purpose of a hypothesis testing is to draw conclusions about broader population based on the results obtained from a smaller sample. So the difference between theory, hypothesis, and hypothesis testing is as follows. A theory is more general. It's just a general explanation of psychological processes, facts, or events. Whereas a hypothesis is a specific, testable prediction about the relationship between variables, often derived from a theory. So you take a piece of the theory and then do tests on it, or you try to infer some new stuff. Hypothesis testing is a statistical procedure used to evaluate whether studies' examples results support a specific theory or hypothesis about a population. So, the core logic, let's go. Finally, away from the definitions. The core idea is that we are evaluating probabilities. We assess the probability that an observed result could occur purely by chance. When you're starting your research, you create an H0 hypothesis. What is this? This is the assumption that there is no effect. So, for example, if you developed a vitamin that would make newborns start walking at 8 months instead of 14 months, your H0 hypothesis would be that your pill has no effect and the babies will not be walking earlier than usual. That would be your null hypothesis or your H0. You then do the experiment and then you check out the results. You calculate the probability or the p-value and determine how likely the results would occur under the no effect assumption. So what this means is you take your normal distribution that you have of the population's parameters. So the way we do it is you have the H0. In our current case, we're just going off of as if we were just testing on the entire population instead of taking samples. So you take all of the population parameters. This is your distribution for your population, and the mean of it is 14 months. You check out that when you have conducted this study with all of the population's babies and found out that when administered this vitamin, the children start walking at 8 months on average, on the mean. You put it in and you check out the probability that the children would start walking at 8 months on your normal population distribution. And when you look at it, you see that it's only 2%. So, under normal circumstances, without any pills, without any alterations to the children, they would start walking at 8 months only 2% of the time. So, that's an incredibly low probability to happen by chance. So, you can say that your vitamin had an effect. If the probability is extremely low, like 5% or 1%, the no effect idea is rejected. So it's all about rejecting the null hypothesis. It's not confirming your hypothesis, but it's about rejecting the null one. So, first of all, what we do is we convert the hypothesis statement into a null hypothesis. So you create a research hypothesis. For example, here we have the null hypothesis says mu1 equals mu2. Mu1 in this case is the mean of the population. The mean of the first population would be equal to the mean of the second population. This essentially means that. So the average. But in our research hypothesis, we're saying that the first population's mean would be lower than the second's. This is what we are claiming. By looking at this, we can see that it's a one-tailed or one-way experiment instead of a two-tailed. Because if it were two-tailed, we would say is not equal to, for example. We then determine the comparison distribution, identify the sampling distribution that would exist if the null hypothesis were entirely true, as we discussed before. We then determine the cutoff score, the critical score that we will say is necessary for our research to be treated as statistically significant. We also call this an alpha value. So this cutoff score that is commonly used is 5% or 0.05. Or maybe if you're more cautious, you can use 0.1% or 1%. And then you determine the sample's score, such as z-score, which we will learn how to calculate on the next part. You calculate the relevant statistical score for the sample and the comparison distribution. And if the sample score lands above the cutoff point within your alpha range, then you can say that your research had an effect, that you can reject the null hypothesis. There are, as I said, one-tailed versus two-tailed tests. If your test only goes one specified direction, so it's either an increase or a decrease, vitamin decreases walking age, for example, then significance level is tested only on one end, like this, 5%. But if it were two-tailed, then we would look at both tails with 2.5, 2.5. It cannot be significant if it's in the opposite direction. So if you claim that your vitamin decreases the walking age and then it ends up increasing it, it shouldn't happen. You can just definitely say that your H1 was wrong. So these hypotheses are non-directional. These two-tailed hypotheses, two-tailed tests are non-directional. It just looks at if there is a difference or not. Instead of just saying there is a lower threshold or there is a higher probability that this will happen, you don't look at any of that. You can just say it's going to be different or not. That's it. So for example, you can, instead of saying this vitamin will decrease the walking age, you can just say this vitamin will have effects on the walking age. It can be negative or positive. So if it then comes out to increase the walking age, then you can say that is also statistically significant because it had an effect on the child, so your H1 is confirmed. Now, of course, this two-tailed test is preferred by researchers because it can help you locate more data instead of just being confined by what you have here, what you tried here. The limitations of significance tests are there because, for example, when we look at 5%, this is just subjective convention. This is not a universal rule. It's all subjective. Also, statistical significance does not mean that your results are practical. I mean, if you had a data where everyone was falling asleep in, I don't know, 10 minutes, and it was entirely bundled up near the mean, and your research concluded that your pill can make people fall asleep at 9.5 minutes instead of 10 minutes, then that could be seen as statistically significant, because your standard deviation could be very low and that could be a statistically significant result. But it doesn't mean that it's practical, because I don't really care if I will fall asleep 30 seconds earlier if I'm having sleep problems falling asleep in 10 minutes. That's what it's trying to say. P-value is not the strength of evidence. P-value is not the probability that the null hypothesis is true. So it's susceptible to p-hacking and selective reporting. So, as everything is. So they use Bayesian analysis instead, which is confusing. Don't look at it. Results denote the statistical procedure used, followed by the degrees of freedom in the score. Who knows what freedom is? Significance is shown via the p-value. Results between 0.05 and 0.10 might be described as marginally significant or approached significance. Results that are not significant are often abbreviated as NS. And in tables, asterisks are commonly used to indicate significance levels. And that's it.